Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to explore the magnetic field created by a bar magnet and the relationships between distance from the magnet and the magnitude of the created magnetic field, to calculate the distance dependence of the magnetic field due to a bar magnet, and lastly to develop a computational model of the magnetic field to compare the on-axis and off-axis magnetic fields from the experiment. My results showed that the distance dependence was negative 2.7 meters and the magnetic moment of the magnet was 2.79 amps meter squared. In this video, I will address the fundamental principles, measurements, calculations, results, and Python code I used in the lab which allowed me to obtain these results. One of the main physics principles used in this lab is the Biot-Savart law for calculating magnetic fields with the magnetic dipole moment mu, where the magnetic field is equal to the equation shown. The distance dependence equation measures the magnetic field at multiple distances from the bar magnet and can be written in the two forms. Lastly, the general idea of magnetic fields and how they work is also important in this lab because we must compensate for the Earth's magnetic north. Otherwise, the results of the magnetic field of just the bar magnet would not be accurate. I used a magnetometer smartphone app to measure the values and compensate for magnetic north. For the measurements of the magnetic field on axis from my experiment, I measured three distances at which the magnitude of Bx equals 20, 70, 120, and 220 microteslas. For the measurements of the magnetic field off axis, we found a perpendicular distance for which the magnitude of B net was equal to 100 microteslas, and then repeated this 3 times to find the average value for each individual measurement. The magnitude of the magnetic field equation is some constant k times the distance r raised to some power n. We should expect the magnitude of the magnetic field B to decrease as the distance r increases, so n should be negative. We have magnetic field values and distance values, so by plotting the natural log of B versus the natural log of r, we should get a straight line with slope n, which is negative 2.7 meters. Next, I solved for the magnetic dipole moment, which is a key distinguishing feature of the magnet and its magnetic field. I started with the equation B equals k times r to the n power. By taking the natural log of both sides, I found the value k to be 7.58 times 10 to the negative 7. After finding this value, I substituted in the values that make up k, which are mu naught, mu, and pi, and solved for mu to get 3.79 amps meter squared. For my Python code for my computational model, I first input the value for the constant mu naught over 4 pi and then created a visualization of the magnet at the origin. I then plugged in my calculated value for mu and created a function to calculate the magnetic fields. I then came up with a scale for my magnetic field arrows and the distance between them. I then created my observation locations for magnetic field arrows for 2 on-axis arrows and 4 perpendicular arrows. Next, I calculated an actual value for the magnetic field arrows by using the magnetic field function I created earlier in my observation locations and multiplied this value by the scale. This final portion of the code creates a magnetic field arrow for an observation location 45 degrees off axis. I used an experimental value in the magnetic field function. This is my computational model. The orange arrows are the on-axis magnetic fields, the blue arrows are the perpendicular magnetic fields, and the green arrow is the 45-degree magnetic field. The calculated magnetic fields are shown at the bottom. The magnetic field at 45 degrees is at distance 1.29398 times 10 to the negative 5, 3.88193 times 10 to the negative 5, 0. Question 1. During the experiment, to compensate for magnetic north, we ensured that the x component of the magnetic field starts at 0 teslas, so that the only value being measured is the magnetic field from the bar magnet. Our results would change because they would no longer isolate the magnetic field's x component. The Earth's magnetic field would alter the x component, which would change each value that makes up the magnetic field, such as mu, k, and n. Question 2. I would expect the magnetic field measurements to be slightly less than double that of just one magnet. When the second magnet is added, the fields would superpose to a larger magnitude. In conclusion, the results found in the experiment were that the distance dependence was negative 2.7 meters, which was close to the value in the Biot-Savart law, which was negative 3. And the value of the magnetic dipole moment was 3.79 amps meter squared. These values were found using the fundamental physical principle of Biot-Savart law.